So this week, focusing on IR spectroscopy and HPLC that we've looked at last year. Right, so we looked at a bit of chromatography last year. Won't cover NMR this week. So understand and use infrared spectroscopy to identify key bonds and functional groups. That's our learning intention, IR. So spectra refers to something to do with light or a spectrum or a graph, right? Scopic, think of that as scopic means to look at, I believe. So wavelength versus we've got large wavelengths or short wavelengths. Don't have to worry too much about that. So what happens is that bonds, covalent bonds is what we're looking at, bonds interact with in different ways to different parts of the electromagnetic spectrum. Okay, so NMR is radio waves. IR is obviously infrared. UV vis spectroscopy is obviously in the UV and the visible, right? X-ray crystallography is obviously in the X-ray region, and so forth, right? So different spectroscopic techniques give us different information because bonds and atoms and electrons, right, change and interact, vibrate, do other things when they interact with these different energies. So if I've got a bond, let's look at hydrogen chloride as an example, it can do one of a number of things. The electronic energy, right? So that's the movement of electrons. So when we excite electrons in a flame for flame tests, that's what's happening. That's electronic energy. It's the energy of the electrons moving into an excited state. We've got vibrational energy. Imagine bonds as not being a static length, but rather it's more like a spring. Yeah? So it lengthens and shortens and lengthens and shortens. We've got rotational energy, right? So a bond is either going to rotate, bend, or stretch. And translational, meaning it moves, the whole molecule. UV vis, AAS was last year, not covered in this course, so you're not going to see any questions on that. Infrared and NMR, most certainly in this course. What we use IR for, I'm going to talk a bit about how it works, but you don't need to know the details of the instrument, okay? So excluding the features of the instrumentation. Don't really use IR at all for quantitative analysis. Yeah? In fact, most of spectroscopy we don't use for quantitative analysis. Chromatography we do. Spectroscopy we don't. Okay. Roughly how it works. Ignore the diagram. We bombard a molecule or a substance with infrared radiation. We have a detector behind that sample, and the detector detects changes to the infrared, right? Radiation going through that sample changes how, and a graph gets spit out. Like I said with mass spec, this whole part of the course, all spectroscopy, IR, NMR, mass spec, are all, right? Look at the graph, make sense of it. Different vibrational energies. If we have a linear molecule, we're looking at back and forth. If we have a bent molecule like water, we can have symmetrical, we can have bending and stretching, we can have asymmetrical, we can have rotational. So essentially what's happening is that the bond absorbs some of the energy, does something, and re-emits it. There's something about energy absorption and bond strength. The stronger the bond, right, the higher the frequency, or we call it the inverse of the wavelength, and it's given this term wave number. So it's not quite the frequency, because frequency is something per second. Whereas now we're just looking at the inverse of the wavelength, which is called the wave number. So we can see there, carbon to carbon triple bond, 839 kilojoules per mole. It stretches, right? That bond vibrates when the wave number is 2300. So the higher the wave number, the stronger the bond, generally speaking. Ignore that for a moment. Things I want you to notice. With infrared spectroscopy, unlike a typical graph, so mass spec goes from lowest to highest number. Notice what, well, let me just ask you, what do you notice that's different about a typical graph? What's different about that? Okay, so you're talking about the shape of the graph itself? Right, what about the graph itself if I remove this? What's different? X-axis is backwards. Yeah? Well, it's the inverse of the wave number. Yeah? So the smaller the wave number, the smaller the wavelength, the higher the wave number. So if I had this as wavelength, it would be 0 plus. Yeah? Not all that important. What's more important is interpreting this, right? Anything that's below around 1500, we can almost ignore. It's called the fingerprint region. It has a particular use that I'll talk about. We've got this thing called transmittance, or the inverse of absorption. So, the top being 100%, the bottom being 0. We've got different absorption bands. I talked about in the pink there, less than 1300, 1500 is the fingerprint region. Ignore that. I'm more interested in anything above 1500. Characteristic of, so in here, for example, we've got single carbon to oxygen, single carbon to carbon, single carbon to nitrogen bonds will have some sort of peak or stretch, as we call it, yeah, in that region. Between 1500 and 2000, carbon to carbon double bond, carbon to nitrogen double bond, carbon to oxygen double bond. Between 2000 and 2500, carbon to carbon triple bond, carbon to nitrogen triple bond. Between 2500 and 4000, carbon to hydrogen single bond, oxygen to hydrogen single bond, nitrogen to hydrogen single bond. The troughs, stretches. I want to talk about them as being stretches. 3 things that we can tell. We can tell what the wave number is. We can talk about its strength, right? So strong means it's a really deep trough, a really long stretch. So we've got strong, medium, small amount of stretching. We can talk about the breadth of the peak. Is it a broad peak? Is it a narrow peak? So broad, narrow, strength, weak, and its position. So its position, its strength, and its breadth. We use IR for the identification of functional groups. So what we're going to do is look at the characteristic IR spectra of each of the different functional groups that we look at in this course. most functional groups, notice how many of our functional groups, aldehydes, ketones, carboxylic acids, all have a carbon to oxygen double bond, right? So there's something characteristic about each of those. O to H we've got in both alcohols and in carboxylic acids, but how that appears on a IR spectra will be different. We'll talk about those. Fingerprint region is really only used to determine the purity of a substance. There's only one peak that we need to look for in a fingerprint region, that if you are given that on an examination, it should be labelled, and that's with a haloalkane. Haloalkane, we can see, is in that fingerprint region. So this is a really important table, right? It's the characteristic wave numbers or absorption bands of each of our different functional groups. Chloroalkanes, alcohols, esters, ethers. Ethers we don't need to worry about, obviously. Alkenes, amides, aldehydes, acids, ketones, esters. Alkanes, alkenes, arenes that we don't need to worry about. O to H acid stretch and O to H alcohol stretch. Notice how they're different. One is broad, one is more narrow. N to H stretch, amines and amides. Very narrow. Right. The intensity. So I talked about breadth, intensity, right, or strength, and its position. C to H, a medium to strong. Carbon to carbon double bond, medium. Carbon to chlorine, strong. Strong and very broad is an O to H in an acid. O to H in an alcohol is not very broad, but relatively strong. So, strong, medium, weak, broad versus narrow, and its position. Three things we can tell. Its breadth, its strength of intensity, and its position. Okay, worked example. Actually, before I go through the worked example, I'm going to switch to a whiteboard and then start talking about the characteristic shapes.